'Cause if I stay with you, girl, wow, 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 things would never be the same. Wow, wow, and I'll just be rambling. Oh, hey. So let's take a look at what would happen if we had two wires that were parallel to one another. So let's imagine for a second I had a straight wire with a current pointing upwards, and next to it I had another wire. Okay? We'll call these I1 and we'll call this I2. Well, if we take a look at the B field created by I1, and since we're looking for a B field created by a wire, we're going to use a right hand rule. We're going to stick our thumb in the direction of the wire's current, and then the way our fingers are wrapping is the direction that the B field is going. So if I take a look at my fingers here, I see that they're wrapping like this, where I'm going into the page on the right side and out of the page on the left side. Look, a little smiley face. Now, this out of the page is everywhere on the left, and this into the page is everywhere on the right. Yes, it's getting weaker because, as we know, Vid47 tells us that the B field itself is equal to mu naught I over 2 pi r, and yes, as we increase B, or as we increase that radial component, the B field's going down, but it's still going in the page everywhere on the right side. Okay? Now, if we take a look at that, what's going to happen to wire 2 then? Well, wire 2 has a current pointing upwards, and there's a B field mapping into the page. So we know that due to a Laplace force, there's going to be a force acting on this wire. It's going to be the current times the cross product of L cross B. So if we take our right-hand rule for this, we put our fingers in the line of the current, and then our fingers are going to curl into the B field. So they're going to curl like that. The B field's going into the page, so I push down. I'm going to see that there's going to be a force on wire 2 acting to the left. There's a force here pulling it to the left. Well, forces can't be by themselves. Forces are equal and opposite interactions, and we're actually going to see that a force is also going to pull wire 1 to the right. And this also makes sense because if I play the same game with wire 2 on wire 1, we say everything due to wire 2 on the right is in and on the left is out. If I do this with wire 2, or with wire 1, I use the same Laplace force. I put my fingers going up, the B field's coming out, so I curl to them. I'm going to see I have a force acting this way, which is this rightward acting force here. Okay? So this attractive force is given by this equation, but it's also given by this. So how can we combine these to make one mega equation? Here's how. So if we start with Vid47, where I know the B field is equal to mu naught, and then this will be the B field created by wire 1. Okay? It's the B field created by wire 1 acting on wire 2. So it's mu naught I1 over 2 pi r, where r is that distance that these are separated by, right? Well, this B here is going to substitute into the other equation. Now, how is this going to look here? Well, it's going to look like the force acting on these wires is going to equal to I. Well, what is this I here? Well, when we did this, this was the I of the wire we were concerned with. It was the wire that the force is acting on. So this was like I2 when we did it. So it'll be I2 times some length crossed with a B field, and we know that B field strength is mu naught I over 2 pi r. And that cross product is a sine theta term here. Now in our case here, our wires are parallel, so we know that our B field is going to be going like in or out of the page, and that sine of theta is always going to be in 90 degrees. So in our case of parallel wires, we just have to say L times the B, which is mu naught I1 over 2 pi r, and then that sine of 90 term in our case is always going to be 1, so we could ignore it. Okay, but it could be there for other things if they weren't exactly parallel. In this case then, if I look at this, I'm going to just leave my L here first. I'm going to have mu naught I1, I2 over 2 pi r. And the reason why I left my L like this is on the left, this is the force. Really what matters with this force is only acting on regions that are overlapping. So if I had a wire setup that had a very, very long wire like this, and then a very short wire like this, I wouldn't use the entire length of this. That wouldn't make any sense. I would only need to use the overlapping region, this length right here. So it actually makes a little bit more sense here to, instead of calling the force is equal to the length, it's a little more sense to say that the force per length, or per unit length, equals mu naught II for each wire divided by 2 pi r. And sometimes I really like to write this as mu naught I1, I2 over 2 pi times 1 over r. And that's because mu naught I and I over 2 pi, these are typically constants. We normally have like a steady state current running through things, and then the only thing that matters to that force is a 1 over r term, which is going to cause that force to decrease. Okay? So that will tell us our force per unit length here, given that we have two wires that are parallel, or if they're slightly offset, we'd have a sine term that we kind of ignored for this one. If your wires are perpendicular to each other, like this and like this, you're not going to get any effect there. You're not going to really care about what's going on because you're going to have 90-degree turns there. Right? Chit chit. Chit chit. Yeah, well, you're still gonna have a force in that way. I stand corrected. You're still gonna have a force there, but these wires aren't gonna exactly pull each other together like you'd imagine. They're gonna kind of just like shift each other around. We're only gonna talk about in this class though 2 parallel wires in this case. So the currents are either gonna be both going up, in which case they're attracted, or if you had a right-hand rule where one was going up and one current was going down, these currents would actually be repelling. The wires would be repelling one another by a right-hand rule. Okay, so that's just a kind of a quick little thing on that. What's going down here. Really, this is the equation we want. And just remember, same direction, you're attracted. Opposite direction, you're repelled. Okay? So for now, this is finished. Adios, everybody. And y'all take it easy. Peace.